Hey guys, this is our video project 11.1 through 11.7, Sequences and Series. I'm Aidan Tan.
I'm Sean Way.
And I'm Andrew Nguyen. What are sequences and series? Sequences are all the numbers in a pattern of numbers represented by the expression a sub n. An example is a sub n is equal to n plus 1, which is equal to 2, 3, 4, 5, and it goes on. Then series are when all the terms of a sequence are added up. For example, we have the summation symbol that goes to infinity when n equals 1, and we have n plus 1, which is equal to 2 plus 3 plus 4, and it goes on.
When we talk about series, we have to find convergence and divergence. Convergence is when the sum of a series is equal to a finite value. If the limit as the series approaches infinity gets to 0, a finite sum is reached. However, there are exceptions to this rule. When we have alternating series, we have to specify absolute and conditional convergence. Absolute convergence is in an alternating series if both the alternating and non-alternating versions of that series converges. Conditional is where the alternating series, but not the non-alternating series, converges. Divergence is when the sum of a series is not finite.
So for our first test, we have divergence test. So as limit from n to infinity, a sub n does not equal 0, then the summation of a sub n will diverge. If the limit as n goes to infinity equals 0, the series does not converge, the test is considered inconclusive. It's a good idea to always use this test first, just in case you can find divergence faster than if you use another test. So for our first divergence test example, we have the limit as n goes to infinity of n plus 1 equals infinity. So this diverges by the divergence test because if you insert n as infinity, then you get infinity, which is not equal 0, so it diverges.
Okay, the second test is now geometric series. If the series is in the format c of n, where c is any constant, then when c is less than 1, the series converges, and then when c is greater than or equal to 1, the series diverges. We can find the sum of a geometric series using the equation s equals a of 1 divided by 1 minus r, where r is the value which is raised to the nth power. So we have worksheet number 3b, and it's the summation symbol for n equals 1 to infinity, and we have 4 to n divided by 3 squared n. So what we do is we find the common ratio, which is 4/9, and then we find the sum by putting it into the equation, and then we get 4/5 as our sum.
Sometimes we can separate our series a sub n into multiple parts. Then we can use the separated version to expand our series and see which terms cancel out and find the sum. One good example of a telescoping series is number 3a on our worksheet. So take this series and find the sum of it. Okay, so using factoring by parts, you figure out that this series can be split up to equal -1 over n plus 1 plus 1 over n minus 1. When you expand it out, you get a whole list of fractions over here. And as you can probably notice, all of these terms cancel out except for 1 and 1/2, which add up to 3/2, which is our sum.
Okay guys, for our fourth test, we have a p-series test. If the series is in the format 1 over n to the p, then when p is greater than 1, the series converges. When p is equal to 1, the series is known as a harmonic series and it diverges. When c is less than 1, the series diverges. So for our p-series example, we're going to find the convergence of the following series of the summation of n equals 1 to infinity of 1 over n to the third. So because 3 is greater than 1, we know that it converges, and also that 1 over n to the 3 is in the form 1 over n to the p. So the series converges.
So here we have the integral test, and we want to set f of x equal to a sub n, and we check for if it's continuous of the interval given, positive at all times, and always decreasing if all those conditions are met. Then we find the integral between n to infinity of f of x and see if it converges. If it does, a sub n converges. If it doesn't converge, then it diverges. If we want to find the remainder of the integral test, we find the integral of n plus 1 and the integral of n, and the remainder is in between those values. So here we have an integral test example, where we have a series where it is 1 over 1 plus n squared. So in order to solve it, we know that the series will decrease because only the denominator grows, and it's continuous because the denominator can never equal 0. The denominator can also never be negative because n squared is always positive. So we can use the integral test, and we find that by using the integral, we set limit of t to infinity and have 0 to t, and then we solve for the integral, and we eventually get pi over 2, which is a finite number. And because that converges, and so does a sub n, which is our series. So here we have the remainder example, which is worksheet number 5, and we want to find the remainder when n equals 10. So we have a series 10 over x squared minus 1 to the 5th. So what we want to do is we want to use the integral test, and then we eventually use the u sub, which is u equals x squared minus 1, and then things will cancel out. It will eventually get to 5 over 4n to the 4th. And then what we do is that we plug in n equals 10, and we get 5 over 4 times 10 to the 4th, and we eventually get 1.25 times 10 to the negative 5th, and that will be our remainder for the series.
Our next test is the direct comparison test. So for this one, you have to find a b sub n that's similar to your a sub n. If b sub n converges and a sub n is less than or equal to b sub n, then a sub n converges. If b sub n diverges and a sub n is greater than b sub n, then a sub n diverges. And if the inequalities are not true, then the comparison test is inconclusive. A great example is number 4c on the worksheet. So just find the convergence of the following series, 1 over n squared plus 9. So because of the plus 9 in the denominator, we can't just say this is a simple p series. So we set b sub n equal to 1 over n squared, which converges because it's a p series, where p equals 2. And we have to figure out that 1 over n squared plus 9 is less than 1 over n squared. And this is true because n squared plus 9 is always greater than n squared. So if the denominator for the first one is bigger, then the whole number is smaller. So this means that our series 1 over n squared plus 9 converges by the direct comparison test.
Okay guys, for 7th test, we have the limit comparison test. If the limit from n goes to infinity of a sub n over b sub n is greater than 0, then a sub n has the same convergence as b sub n. If not, it is inclusive. Okay, for our first example problem, we have the problem from the worksheet number 4d, find the convergence. So we have the summation from n equals 1 to infinity of 4n squared over n cubed plus 2n plus 7. Okay, for our explanation of the problem, to find b sub n, we take the highest power of the numerator and divide it by the highest power in the denominator. So for this problem, we use n squared over n cubed, which is the same as 1 over n. So b sub n equals 1 over n. B sub n diverges because it is a harmonic series when the p series where p equals 1. So we set limit as n equals infinity of 4n squared over n cubed minus 2n minus 17 over 1 minus n, or a sub n over b sub n. And that equals the limit as n goes to infinity of 4n cubed over n cubed plus 2n plus 17. And that goes to the limit as n goes to infinity of 4 over 1 plus 2 over n squared plus 17 over n cubed, which is also equal to 4. And 4 is greater than 0. Because b sub n diverges and the limit comparison test passed, the summation from n equals 1 to infinity of 4 sub n squared over n cubed plus 2n plus 17 also diverges.
So here we have our 8th test, the alternating series test. If a sub n is an alternating series which has negative 1 to n sine or cosine, set b sub n equal to the non-alternating version. If b sub n is always decreasing and the limit of b sub n has n approaches infinity equals 0, then the original a sub n converges regardless of whether b sub n converges. We can also use AST to determine accuracy, where we set b sub n less than to the value for accuracy and solve for n. Unfortunately, AST by itself does not tell us about absolute or conditional convergence. So here we have an example, worksheet number 4b. It is negative 1 to the n times 3n squared plus 6n plus 1 divided by n to the 4th. So what we want to do is, we know that negative 1 to the n lets us know that is an alternating series. And then we want to divide the highest parts in the numerator and denominator. We get n squared over n to the 4th, which is the same as 1 over n squared, which is now our b sub n. And the derivative of 1 over n squared is negative 2 to the n cubed, so now we know that b sub n is decreasing. And then we set the limit as n goes to infinity, and we get it's equal to 0, so that means the series converges by AST. So now we must check the series for absolute convergence, so we'll use a limit comparison test with b sub n equal to 1 over n squared to check for convergence. And then we use the limit comparison test, and we eventually solve it, and then we get to 3, which is greater than 0, so the series does converge by a limit comparison test. And because the alternating series and the non-alternating part converge, we have absolute convergence. So here we have worksheet number 2, and it asks us to find the remainder to be accurate to 0.01. So the series is -1 to the n times n plus 1 over n cubed. And because it's n over n cubed, which gets us 1 over n squared, which will be our b sub n. So we want 1 over n squared less than 0.01, which can be written as 1 over n squared, which is less than 1/10, which cross multiplies to 10 is less than n. So we need at least 10 terms to be accurate to the 0.01.
If L is less than 1, the series is absolutely convergent. If L is greater than 1, the series is divergent. And if L equals 1, the ratio test is... One example where we can use the ratio test is 4e on the worksheet. Alright, so to do ratio tests, we set limit as n approaches infinity of absolute value of a sub n plus 1 divided by a sub n, which simplifies out to limit as n approaches infinity of absolute value of -1 times 2 times cube root n times over 4 times cube root n plus 1. So we divide everything by cube root n, and that ultimately simplifies out to absolute value of -2 over 4, which is 1/2, which is less than 1. So this series is convergent by the ratio test.
So our 10th test is the root test, in which we have 3 conditions. The first condition is where the limit as n goes to infinity of the nth root of absolute value of a is less than 1, then it absolutely converges. If this limit as n goes to infinity of the nth root of absolute value of a is greater than 1, then it diverges. And if the limit as n goes to infinity of the nth root of absolute value of a is equal to 1, then it's inconclusive. So for our first example, we have the worksheet problem number 4a, in which we find the convergence of the following series. We also have to include conditional or absolute convergence when necessary. And the example is the summation of n equals 1 to infinity of 2 to the 2n plus 1 over 6 to the n times square root of n. So to explain the example, we take the limit as n goes to infinity of 2 to the 2 plus 1 over n over 6 times the 2n, the 2n root of n equals 4 over 6, which is less than 1. So it absolutely converges by the root.
Alright, so here's some extra practice, which is number 1 on the worksheet. Just find the convergence of the following series. And let's start with the answers for part A. So looking at this series, you can use the second difference to figure out that the series can be rewritten as 1 over n squared plus 2. So when we use the direct comparison test, we set b sub n equal to 1 over n squared. And this converges because it's a p series where p equals 2, and 2 is greater than 1. So then we have to figure out that 1 over n squared plus 2 is less than 1 over n squared for us to reach a conclusion. And this is true because the denominator of the original series is always greater by 2. So our original series is going to converge by the direct comparison test.
So here we have 1b, which is 1/2 plus 2/5 plus 3 times plus 4 times 6, and so on. And the numerator is n, which you can notice by looking at how the numerator changes. Then you can find the second difference between the denominators and the series, which equals 2, which means that the denominator of the series is an n squared function. And then after playing with some numbers, you figure out that the series is n over n squared plus 1. So here we have b sub n, which equals 1 over n, and we know that it diverges by a harmonic series. So we try to find the limit as n goes to infinity for n over n squared plus 1 over 1 over n. And we try and find that the limit as n goes to infinity equals n squared over n squared plus 1. So then we get that it simplifies out to be equal to 1, which is greater than 0. So b sub n diverges, and then that means the series will diverge by limit comparison test.